This is my video report for Lab 5. I have chosen to investigate an elastic collision for this experiment. I observed a basketball bouncing on the ground. Initially, the ball was released from rest, and I have observed it bouncing on the ground until its full stop. The distance from which it was dropped is 1 meter and delta t equals to 5.5 seconds. The most important concepts used throughout this experiment are pretty standard. Newton's second law, position and velocity update equations, gravitational and net forces along the y-axis. But in addition to that, I have introduced elastic collision and the coefficient of restitution. So in order to achieve our final goal and investigate an elastic collision, I want first to introduce the coefficient of restitution concept, which describes a ratio of relative speed after to the relative speed before the collision. If the coefficient is 0, it means that the collision was perfectly inelastic and the two objects either stopped or continued the motion together as one whole object. In the opposite case, if the coefficient of restitution is 1, it means the collision was perfectly elastic. You might pause the video now and read this slide for more information on coefficient of restitution. In order to get a more accurate result, I have decided to calculate the coefficient of restitution in each collision and then calculate the average from the obtained values. For this experiment, I have also decided to analyze only the first 3 bounces. So since in our case the second object, the ground, has a constant velocity of 0, the new formula for the coefficient of restitution is velocity of the ball after the collision divided by the velocity of the ball before the collision. And after performing a few simple operations, we obtained an average value of 0.57. Note that the velocity values of the ball before and after each collision were obtained from Tracker. As the first part of my experiment, I have analyzed the video in Tracker to obtain a predicted model of the position versus time graph. I have set the distance to be 1 meter and have placed the origin of the coordinate axis and the initial position of the ball. And finally, I have followed the ball's motion with the center of mass tool to obtain all the data needed, such as the velocity, time, and the y-coordinate of the ball's motion. Then I have used the GlowScript code to build a computational model for the ball's motion. On lines 31 through 60, I have initialized all necessary values and constants. Also, I have created a block of code that allows me to upload the CSV file with data obtained from Tracker, so I could plot both models and compare the behaviors of the graphs. On the line 67, I have created a recursive loop to update position, velocity, and force. However, this code is a little bit different from everything I had to code for the previous labs. On line 69, I have used a conditional statement to upload velocity using the to update velocity using the coefficient of restitution. And then, in the very end, on the lines 87 through 92, a block of code that allows us to compare video analysis with the computational model. In conclusion, on this side, you can see the comparison of the two models. The red graph shows the predicted model and the blue graph shows the computational model. On the screenshot on your right, there are 3 collisions that describe general trends of the motion. As expected, the motion before the first collision on the two graphs is almost completely identical, since it can be described by just Newton's second law. Later, as time goes, the graphs start to differ since a lot of factors such as human and environmental errors affect the results of the model predicted via Tracker. Lastly, one can notice that each next bounce reaches approximately half of the height of the previous bounce, and this pattern is due to coefficient of restitution, which, as we calculated earlier, is equal to 0.57, which is approximately 1/2. And this is it for Lab 5. Thank you.